Unit 2A, Organizing Data Distributions. Here's a distribution of raw data compiled from 12 students. We asked the student, how many courses did you pass last semester? We take a survey of 12 students, and we ask each student, how many courses did you pass last semester? The first student says 4 courses, the next 4 courses, the next 2 courses, and so on. The data in this form is called raw data. Raw because we have not done anything with it. It's not very useful in this form. You can imagine if we had 10,000 students in our sample, we would have 10,000 numbers like this. It would be very difficult to get meaning out of it. One thing we could do is sort the data to put the scores in order. So we could put them in order either lowest to highest or vice versa. Let's start with the lowest. 0, 0, 1. We have 2, 2, 2, and 2. We have 4 2s. Then we have 2 3s. And we have 1, 2, 3 4s. Well, this is a sorted distribution. This would be more useful than just the raw data. Here's the sorted distribution. Sometimes they're put into a table like this. We put X on top because we think of the number of courses people tell us that they passed as scores, and the abbreviation for score is X. So X has the value 0 for one student, it has a value of 0 for another, it has a value of 1 for another, and so on. So this is called a sorted distribution of the scores, or a sorted distribution of the X's. When we have them in a chart like this, frequently we leave one space at the bottom for totals. So we could sum up the X's. We could take the sum, sigma, uppercase sigma is the symbol for sum, which means add the X's, sigma X. So if we add these scores, we would get 4, 8, 12. 12 and 8 more is 20, 22, 24, 26, 27. 27 would be the sum of the scores. So sigma X, the sum of the scores is 27. If we wanted to get an average, we could get the sample mean. And that's just the sum of the scores, the sum of the X's, over the number of scores. The symbol for the sample mean is X bar. The symbol for the sum of the X's is sigma X. And the number of scores is the sample size, N. So we could write this as a formula, X bar equals sigma X over N, and we'll be seeing this formula a lot throughout the course. If we wanted to evaluate this, sigma X was 27. If we divide that by the number of scores, we remember from the previous slide, N was 12. And if you divide 27 by 12, you get 2.25. So the sample mean would be 2.25. We could also make a frequency distribution from these data, because if you had 10,000 scores, you would not want to have a column of 10,000 numbers. So a frequency distribution is a nice way to summarize these data. So the scores we have are 0, 1, 2, 3, and 4. We put that in one column. And in the other column, we put down the frequency. The frequency means how many times the score appears in the distribution. So notice that there are 2 zeros, so the frequency of 0 is 2. There is 1 1, so the frequency of 1 is 1. There are 1 2 3 4 2's. The frequency of 2 is 4. There are 2 3's, and there are 3 4's. This would be a frequency distribution chart. This is the frequency distribution chart we just made. We often have another row on the bottom for totals. Now, if you total the x's, you get 4, 7, 9, 10. And if you total the f's, we get 5, and 5 is 10, and 2 is 12. Now, are these numbers meaningful? Well, if you remember, we had 12 scores, so this looks good. And the total of the scores was 27. So where does this 10 come from? Well, this 10 does not have any meaning. So therefore, please remember that we do not take the total of the x column in a frequency distribution. It does not have any meaning. On the other hand, the sum of the frequency column, sigma f, I could write it using our shorthand, the sum of the frequency column is always equal to the sample size. So that's important to remember. We do want to sum up the frequency column because that gives us the sample size, which was 12. We could also make a cumulative frequency distribution from this sample. The way we do that is we have an x column. The scores again are 0, 1, 2, 3, 4. And instead of putting frequency in the next column, we're going to put the cumulative frequency. I'll abbreviate it, cumulative frequency. And what this means is the number of scores now I can either say less than x or less than or equal to x. I'm going to use this symbol, less than or equal to x. If I just use less than x, I'd have a slightly different chart. So anyway, let's start in the middle. Let's start with 3. The cumulative frequency for 3 is the number of scores less than or equal to 3. Well, here's 3. How many scores are less than or equal to 3? Well, these scores are all less than 3, and these are equal to 3. How many scores is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. So the cumulative frequency of 3 is 9. Let me go back and start in the beginning. What is the cumulative frequency of 0? How many scores are less than or equal to 0? Well, there are no scores here less than 0. But how many scores are equal to 0? 2. So the cumulative frequency of 0 is 2. How many scores are less than 1 or equal to 1? Well, these scores are less than 1, and this one is equal to 1, so there are a total of 3 scores that are less than or equal to 1. What about 2? These 3 scores are less than 2, and these 4 scores are equal to 2, so therefore there are 7 scores that are less than or equal to 2. And finally, we did 3 already, so let's go to 4. how many scores are less than 4? 1, 2, 3, 4, 5, 6, 7, 8, 9. And then how many are equal to 4? 3. 9 and 3 is 12. That would be a cumulative frequency distribution for our data. Here's the chart we just made. Now the question is, would it make any sense to put another row on here for totals? Would it make any sense to total the x's and get 10 again? Well, just as before, that's going to be meaningless in this particular case. Would it make sense to sum up the cumulative frequency column? Well, that's going to be 12 and 12, 24, 33. Does that have any meaning in this problem? No. So with a cumulative frequency chart, do not sum the columns. That would be meaningless. We could also take the same data and make what is called a relative frequency distribution. This should be an E here. Relative frequency distribution. Relative means compared to something else. So the relative frequency is, I'll make another column here, it's the frequency relative to or compared to the sample size. The relative frequency is f over n, f divided by n. So in this case, to get n, we could sum the f column. Remember, the sum of the frequencies is the sample size, isn't it? So 5, 9, 10, 12. So n is 12. So to get the relative frequency, we're going to take the frequency and divide by 12. So take the frequency 2, divide it by 12. Take the frequency 1, divide it by 12. I'm taking this column and dividing it by 12. 4 divided by 12. 2 divided by 12. 3 divided by 12. So that's the way you would make a relative frequency distribution chart. Now, you could write this in different ways. I could write f over n, the relative frequency, in different ways. I could, for example, I could change each of these fractions to a decimal number. So 2 divided by 12, that's going to be 0.1666, like this. Let's round it off to 2 places. I'll call that 0.17. And we could take now the next one. This should be a 12 here. 1 divided by 12. That's going to be 0.08333, like that. Let's round that off to 2 places. 0.08. 4, and proceed the same way with the rest of them. 4 divided by 12 is going to be 0.333, repeating. I'll round that off to 0.33. 2 divided by 12, we had that already up here, 0.17. And 3 divided by 12, that's a quarter, 1/4, or 0.25. So that's the relative frequency column in the form of a decimal. It could also be a percent. To change a decimal to a percent, you merely move the decimal point 2 places to the right. So 1700ths is 17%. 800ths, 8%, 33%, 17%, and 25%. Now, if you sum the relative frequency column, what do you get? Well, if you take the percents, we have 15, 25, 30, 4, 7, 8, 10. This adds to 100%. If you take the decimals, you're going to get 1.00. And if you add the fractions, the denominator is 12. If you add the numerators, you're going to get 12. 12 twelfths is 1. So notice that the sum of the relative frequencies always comes out to be 1 or 100%, which is the same as 1. So this is something that we want to keep in mind. Later on, we're going to call these kinds of distributions probability distributions. And with the probability distribution, we're going to think of f over n as the probability of x. This is something that happens later on in the course. And we're going to see that the sum of the probabilities in a probability distribution always comes out to be 1. So that's something in the future we're going to be dealing with. Here's the table, the relative frequency distribution table again, just with f over n in the form of a fraction. So again, remember about the totals. Would it make sense to total the x column and get 10? No. Would it make sense to get the sum of the relative frequency column? Well, if you add them, the common denominator is 12, you add the numerators, 2, 3, 7, 9, and 3 is 12. That equals 1, and that's what we expected. We expected the sum of the relative frequencies always to be 1. Next, we're going to group the data into classes or intervals. So we'll take the scores, and we're going to group them together in the following way. We're going to take all the scores from 0 to 1 and put them together. All the scores from 2 to 3 form the next group or class, and all the scores from 4 to 5 form the next class or interval or group. And we're going to put the frequency for each group. So when I say the interval from 0 to 1, I mean all the scores between 0 and 1. There are 3 of them. So the frequency of that first class is 3. The next says all the scores from 2 to 3. 2 to 3 would be all these. How many are there? 1, 2, 3, 4, 5, 6. 6 is the frequency for the next class. And finally, the last class, 4 to 5, there are 3 scores there. So this would be a frequency distribution for grouped data. Here's a nice picture of what we just did. Now I could take this chart and put another row on for sums. Would it make any sense to sum up the x column? No. Would it make any sense to sum the frequency column? Yes. The sum of the frequency column is equal to the sample size, which in this case was 12. Well, we've looked at the same data in many different ways. And now let me show you another way to organize data, but we'll take some different data for this example. This is called a stem and leaf plot. What we can do is take our scores. So here we have some scores. We have 1, 2, 3, 4, 5, 6, 7 scores. So n is 7. Sample size is 7. And what we're going to do to these scores is make a stem and leaf plot. The way that works is you chop off the last digit, the ones place digit, from the data. And you look on the left side. If there's nothing there, you put a 0. On the left side, what you have are called these stems. So the stem goes on the left side of your picture, and the stems are 0, 1s, and 2. So you put 0, 1, and 2 for the stems. And now for the leaf part, well, record this first number, 0, 0, as 0, 0. 0 is the leaf. The next score, 0, 6, 0, 6 is the leaf. How do I record 10? 10 is 1, 0. Notice, the way I record 12 is I only have to put a single number down. The 1 is there, the stem is there, I just put down the 2 to make 12. How do I record 12 again? Just put a 2 next to the 1 stem. 15 would be 1 and then 5. 22, 2 and then 2. If you sort the distribution first, then these come out sorted. If you did not sort the original distribution, the leaves are usually sorted, so we try to put the leaves in order of size. So this would be a stem and leaf plot. It's a little bit like a bar graph, I guess you could think of it that way, with the bars horizontal instead of vertical. Now that may not seem worth it, but let me give some more examples. Here's the stem and leaf chart for some other data, and let me transform this back into the sorted data. This first entry means stem is 3 and leaf is 8. That means 38. This means stem is 3, leaf is 9. This 0 corresponds to 40. This 2, 42. This 7 is 47. Get the idea? 5 followed by 1, 51. Another 51, etc. Down to 9 followed by 5. 9 followed by 6. So this stem and leaf chart is a pictorial representation of all these scores. And then the question says, what is the maximum or biggest data entry? Well, the biggest data entry would be 96. It's the last entry on the bottom, 96 by 6. So the answer would be 96 or A. Suppose I asked you, what is n equal to in this case? What is the sample size? Well, you could write all these out, or you could just add the leaves together. How many leaves do we have here? We have 1, 2, 3, 4, 5, 6, 7. Then we have another 7. Then we have 6. Then we have 5, 4, 3, 2 and 2 is 6, and then 3 more this way. So we could add these together, and what do we have? We have 9, and 9 is 18, 3, 21, 27, 34, looks like 41. It looks like n is 41. Here's some new data. 100 people have their blood tested, and a particular chemical in their blood is measured, and the readings are listed as follows. So, for example, one person had a level of 399 for this chemical. Another person was 369. Another one was 403, and so on. We want to get some meaning from this data. These raw data, the way they are here, it's impossible to get any kind of feeling for these scores. So what could be done is make a stem and leaf chart for these data, and you'd have to look at the size of the numbers. They go from about 300 to 450 or something like that. So you would chop off the last digit, and this first part would be the stem, and then the leaf would be this single digit. So we're going from a stem of 30 down to about 45 or something like that. 33, 34, 35, 38, 40, 41, 42, 43, 44, like that. So you put down the stems. Now, once you have the stems, now we're going to put down the leaf. So let me start on this side. Chop off the last digit. So I'll do this first column. 363. 363 would be represented like that. 410. 41 with a 0. 369. 369. 371. 371. 449. 449. 368. 368. 300, 300, 372, 372, 421, 421, 367, 367, etc. You'd have to do the rest yourself. And what kind of a picture would you get? Well, you get this picture when you're done. What's nice about this picture, it does give you a shape. Kind of a mound shape here, especially if you think of it rotated this way. So it's a mound shape, or later on we're going to see it's a bell shape distribution. That's going to be an important distribution for us later on. That's the end of Unit 2A. See Unit 2B for organizing data by making graphs.